Okay, that's fine. Yeah.
Okay, let's start. It's about the time. Hello, everyone, ladies and gentlemen. Welcome to the section Theoretical Computer Science. So today we will have 3 talks in this afternoon. So the first speaker will be Professor Ravi Ramamoorthi, right?
Yeah.
From University of California, San Diego, and NVIDIA, right?
Yeah.
And he will talk about sampling for view synthesis from local light field fusion to neural gradients, field, and beyond. Okay.
Okay, thank you. And also my co-author, Rodrigo Ortiz-Queon, is also here for the conference. I also want to put up a slide of the co-authors of the original paper. This is their affiliations at the time the work was done. I mean, since then, some students have actually graduated. You can also see that all of them look a lot younger than we now. So the goal here is to be able to take a few images like this with your cell phone and capture images such as this, a few images of the scene. And after that, be able to view the scene immersively, such as in applications in virtual and augmented reality, as if you were actually present in the scene. So to be able to lift 2D photography to a full 3D immersive experience. And you notice here that you get the reflections from the puddle, you get the reflections on the bike, and you actually feel as if you are immersed in the scene. This is a robust technique that can handle a wide variety of scenes. In these cases, you see plants, you see foliage, you see the reflections of cars, you see people. Okay. And Rodrigo just walked in, who's also a co-author of this paper. Formally, this is a problem that's often referred to as novel view synthesis. So you're taking a number of images around the scene. Thereafter, you have some scene representation, and much of the challenge since this problem was formulated 30 years ago has been in finding the right scene representation. And once you've done that, you seek to be able to render these novel views, create these nice fly-throughs, be able to really perceive the scene as a 3-dimensional entity rather than simply a 2D photograph. This entire problem can also be formulated, at least conceptually, in terms of what is known as the light field. Now, a light field, like many of the physical concepts, and of course, this is the International Congress on Basic Science, the light field is a concept that well predates computer graphics or computer vision, and in fact, I mean, goes back at least to about the 1940s and Gershen's and Moon's idea of a light field, and actually even earlier to the early 1900s. The idea is that if at each point in space, 3-dimensional space, and each direction, which is a 2D directions of the unit sphere, you can measure the light flowing through. Technically, this is the radiance, and the units are watts per meter square steradian. That's not important in the rest of the talk. Now, if you could measure the radiance flowing through each point and in each direction, then you can effectively reproduce images of the scene from any location and looking in any direction, because for each ray that goes into the scene, you have recorded what the radiance is. Now, in a famous paper that Levoy and Hanrahan had on light field rendering in SIGGRAPH 96, from which I've taken this slide, and simultaneously also the work by Gortler et al. On the lumograph in the same year, they showed that in free space, because the radiance remains constant along a straight line, you can reduce 5D to 4D, and you can parameterize it in a number of ways. This now allows you, if you capture this 4D light field, to get images in the exterior of the convex hull of an environment or in the interior of an environment. Moreover, images can be viewed as 2D slices of this 4D light field, and you're effectively inserting the acquired imagery in the representation of the 4D light field, and extracting an image is effectively taking a 2D slice of the 4D light field. Now, for purposes of visualization, it's easier to do this in flatland. So instead of a 4D light field, we actually have a 2D light field, and an image is a 1D collection of rays. You can capture this, for example, by taking a camera and in a circle or in a plane around an object. And of course, I mean, it's trivial to interpolate the individual camera positions, but because radiance remains the same along a straight line, you can do even more interesting things such as zoom into this picture as shown here. And when you zoom into the picture, you want to be able to reproduce the image, you just have to resample the rays that may come from multiple source cameras, but you all have all of this information in the light field, and in fact, you can produce any view from any direction looking around the object. So how do we capture these light fields? And until that time, what had been demonstrated is that if you have a very dense sampling, you can actually get robust results. And this is quite an engineering feat. It's the Stanford multi-camera array project led by Professor Leboy. And it has, as you can see, a 10 by 10 array of cameras. It's kind of a giant beast. And in fact, PhD theses have been given for just calibrating this object. But if you have the resources to build something like this, then you can actually reproduce a light field. This has inspired a lot of subsequent work. In fact, my alumnus Ryan Oberbeck had this paper just before the work for which the award is given, which is Google's Welcome to Light Field demo. And it's a bit less heavy than the camera array, in the sense that you have a rotating set of cameras. And given that, you can produce these kinds of nice images, but it requires considerable setup and fairly dense sampling. What this paper asks the question, how do we achieve robust, high-quality results with sparser, casual input view sampling like you may do in a cell phone? Here is an example of what you're trying to do, where you are trying to acquire images just with your cell phone on a 5 by 5 grid of cameras, but they don't even have to be perfectly regular. This is kind of a semi-regular grid that a user can just go out and manually capture, like I showed in the first slide of this talk. What we do is promote each sample view to a local light field that then enables you to locally create these kinds of view synthesis results. Furthermore, by blending the nearby local light fields together to render novel views, we support a much broader baseline and much larger changes in terms of the viewpoint. Again, notice the reflections in the puddle of the bike, that we are able to capture these complex and visually interesting results. Now, the representation we use is something referred to as a multiplane image, as a local light field representation. This has actually a long history noted here, and Zhu et al. Popularized it the previous year in work where they took two images and tried to extrapolate. As is clear from the name, a multiplane image effectively has a set of planes stacked fixed distance apart, and on each plane you have an RGB color and an alpha or an opacity. So now you can composite these planes together to get the final image. One of the key things that had happened by this time is that the first deep learning-based algorithms for view synthesis had come out. And so our question was whether we could leverage modern deep learning algorithms in a view synthesis pipeline. The multiplane image was ideally suited for this because the samples are stored on a regular grid. And that means the convolutional neural networks that were popular at that time and still are used can easily predict these planes, which are just images. Moreover, this is a 3D representation of the light field that is persistent across views. So in the history of light field rendering, one thing people have wanted to do is say, look, like I can just take these bunch of views, I don't need any intermediate representation, can I produce a new view? And historically, that has been very challenging because without any insight into what a three-dimensional scene is, it's very hard to do. In this case, the multiplane image is a consistent 3D representation of the scene, and that enables you to consistently create new views of the scene. In order to train a deep learning pipeline, or even a conventional pipeline by optimization, you want the rendering process to be differentiable, which it is in this case. And it can therefore be supervised simply by using held-out views. Effectively, you train it to get the multiplane image, and it must be able to predict the other views and the held-out views. Going back to our first goal, which is to promote each sample view to a local light field, what you do is you take the view, you take the neighboring views, and then you use the neighboring views as inputs to predict the multiplane image for each view. This prediction step is done using a deep learning pipeline, but this paper is actually not primarily about deep learning or AI. It is primarily about a sampling theory analysis that gives you a rigorous ground for how far apart your views need to be. So this is just a small part that relies on deep learning to create the multiplane image, but it is not actually primarily a paper about deep learning. So you predict the multiplane, and in fact, if you had an alternative technique to predict multiplane images, you could just drag and drop that here. So you use neighboring views as inputs to predict the multiplane image for each view. And because you are really predicting a physically based representation, you don't need a huge data set. So 99% of the training data is just synthetically generated. You don't need a real-world big data set. And you just do a little bit of fine-tuning on a small real data set of only about 25 scenes. And this is what these scenes look like. This is an example of the views you have on fine-tuning. So that's all as far as the basic algorithm and a little bit about talking about the learning part of it is concerned. Most of this paper is about this question. How densely do we need to sample the input views to reconstruct the local light field, to reconstruct the light field? So you can sample it sparsely, you can sample it more densely, and how do you know how many views you need? In order to do this analysis, we create this visualization that's sometimes referred to as an epipolar plane image. And broadly, what it is again, because we have a hard time looking at 4D quantities, we simplify them into a 2D quantity where one dimension is the view dimension as the camera moves, it's this dimension here. And another dimension is the pixel dimension. Again, pixel is a 2D image. You look at one scan line. So you can think about this as a flatland light field. The camera views, and it's imaging the scene like this. Now you can imagine as the camera moves, these points will kind of move in the opposite direction depending on their depth. And that is in fact kind of what you see here, right? So if you see the same color or the same point, it has a sheared line because at different viewpoints, it will be at a different pixel location. That is referred to as disparity. As you close one eye, close the other eye, depending on how close the objects are, they're going to shift a little bit. And that is referred to as the disparity. It can just be measured in pixels. The depth also kind of gives you the slope of this, which is, formally speaking, a shear. You notice here you have what is an occluder, an object closer than this plane. So if we had this yellow object here, and the disparity for this object is more, which means its slope is larger, and because it's in front of this plane, it actually occludes the plane. So this is the typical structure of an epipolar plane image. So here's the camera sensor, and here is what the epipolar plane image looks like. And as you sweep the camera through, you are effectively getting one scan line of the epipolar plane image. We can also analyze this in the frequency domain or the Fourier domain. So first, let's just talk about this plane here. Here, the slopes are all the same. You get this kind of shared representation. In the Fourier domain, you actually just get a line. And that line is going to actually be orthogonal to the direction around which it's constant. So if you look orthogonally to the line, this is constant. And because it's constant, there is no frequency spread. You only get the DC or the constant term. That's why it is a line. And the extent of the line in the frequency domain depends on the extent of the frequencies and the texture that typically is determined by pixel sampling resolution. Now, what happens because of your occluder? So you can think about the occluder as first multiplying the original signal by this visibility mask, and then adding in the occluder itself. Okay. So it is a multiplication by the visibility mask. Now, this is the occluder's light field Fourier support. Notice that the occluder is something like this. So it is itself going to have a Fourier support orthogonal to this. And because the depth is closer, the slope is going to be larger. So here is the occluder's Fourier support. But then you are multiplying in the primal domain by the mask, which in the frequency domain becomes a convolution. So you're effectively convolving with the occluder's Fourier support. And that's what the kind of convolution looks like. And now your light field looks like this parallelogram structure. And finally, you have to add in the occluder's light field, which is just the central line in this parallelogram structure. So looking at this structure again, it is determined by the slope of the closest occluder, and there you can see that that line depends on the slope of the furthest contents support. So what we've done at this point is that we have understood the frequency analysis of what the scene's Fourier spectrum looks like. Now, what happens is that you will sample the scene, and in Fourier theory, sampling actually brings down replicas of the central spectrum. The reason for that is sampling is effectively a comb spectrum. So you're multiplying in the primal domain by this comb spectrum where you sample at discrete locations. The Fourier transform of a comb is also a comb. The width is inverse to the spatial width. And now you're convolving in the frequency domain with this comb, and each comb spike brings down a replica of the original spectrum. So ideally, if your sampling rate should be this optimal minimal sampling rate, so that these replicas touch but don't overlap. If that happens, in your reconstruction filter, you can isolate the central replica and recover the original signal. So this is effectively the view sampling frequency to avoid errors or what's technically known as aliasing. So that's a lot of math and a lot of Fourier analysis, but it also has a very intuitive explanation. Okay, which is the Nyquist sampling theorem. And the sampling theorem, you may have thought about it, you need two samples for each frequency that you're trying to capture, so depending on the maximum frequency. But it has a very intuitive explanation in the context of view synthesis, which effectively says that the disparity of the closest content has to be less than 1 pixel. What that means is if you look at the closest point and you move from one camera to the next, it can shift by less than 1 pixel. If that happens, the Nyquist sampling criterion is met, and you will be able to do view synthesis without aliasing. However, when you work out what this condition is capturing a scene with the closest content half meter away for viewing on current VR headsets requires that you have an image every millimeter. Okay, so this is not practical. So the next question is, this is assuming no scene representation. Essentially, you're not reconstructing the scene or doing anything with it. But now coming back to our case where we have ideal multiplane image layers for each view. So in this case, the scene has been broken into these kind of depth layers. And intuitively, what you can think about is within a depth, if this depth is accurate, then you can reproject. So when you talk about the disparity of the closest point, you are effectively kind of reprojecting, as you're making no assumption about the scene depth. So your default assumption is that the scene depth has disparity 0, which will be satisfied for points that are infinitely far away. So effectively, you're reprojecting the scene to a surface that's infinitely far away. But what you can do here is you can make the assumption that the scene actually lies somewhere in the middle. So it's technically the harmonic means, the optimal way to put it. And now you reproject from one camera to the next, assuming this depth. And now you only have to consider the disparity with respect to this mean depth. And that isolates the disparities a lot better. So formally speaking, you can think about these different disparities. You can think about the Fourier spectrum. And if you just think about the Fourier spectrum for this narrow range of depths, the Fourier spectrum becomes a lot more narrow. And the narrower Fourier spectrum means you can pack more of them together, and you can have a sparser sampling. In fact, this observation is not new to this work. It actually goes back to a seminal paper from Chai et al. In SIGGRAPH 2000. Work was actually done in Beijing by Microsoft Research Asia. It was probably one of the first SIGGRAPH papers coming from China. And they made the observation here that you have this double wedge spectrum. So they didn't actually consider occlusion. With occlusion, this double wedge fills out to be a parallelogram. So you have and so here in their case, the double wedge is determined by the minimum and maximum depths and all the depths in between. Now, because of sampling, these pack together, but you can reconstruct the central spectrum using this parallelogram filter. And they actually had a joint image and geometry minimum sampling curve, which said the more accurate your geometry, in some sense, the more depth layers you have, the fewer images you would need. So you can reduce from 1,000 images to, in their case, I get 16 images or even 4 images. And we similarly will make the observation that you can reduce by a factor of 64 in both dimensions because you have 64 depth layers in the multiplane image, which will give you a net reduction by a factor of 4,000. And that's why we're able to do 20 to 50 images. Okay, so here is our view synthesis quality versus the minimum disparity. Okay, so LPIPs and better will be lower values of LPIPs. It's a common image metric. So here is the Nyquist sampling. If you actually sampled it so that your disparity was maximally 1, you would get a very low LPIPs value. So now here is what happens when we use the multiplane image to predict 8 planes. Because within each plane, the disparity is now 1, even though the total disparity is 8, with 8 planes, you are still able to do Nyquist sampling. And so if you are able to predict a multiplane image with 8 planes, you can now handle a disparity of 8 pixels instead of 1 pixel. Similarly for 16, 32, and 64. This is really a key result, that you can use this simple pipeline to predict a 64-plane multiplane image. And that reduces the sampling rate you need in each dimension by a factor of 64. Because cameras are in 2 dimensions to capture the 4D light field, you get a net reduction by a factor of 4,000 in the number of images you need. And this allows you to create high-quality results with 25 to 50 images, where we have given you precise conditions for how far apart the images have to be sampled, and that can be implemented even in a mobile app that tells you where to capture the images. Of course, the question is, can you go on and have 128, 256, 1 million layers? And the answer is no. At some point, the multiplane image depth recovery is not accurate. And at 128 pixels, the individual images, when the disparity is that large, they don't see enough of the scene to actually be able to predict the multiplane image. So we're really only able to go up to 64 layers. Here is the prescriptive guideline. You sample the scene with a 64 pixel disparity. You reduce the number of views with 4,000 relative to the Nyquist rate. And this enables you to produce images like this, where you have a wide variety of scenes. And here are more examples. Foliage, you have glossy reflections, specular highlights, interesting complex objects, humans, etc. So that is as far as local light field fusion is concerned. Now, that paper was 5 years ago, so I quickly want to talk about newer work in this area. This slide is courtesy of my PhD student, Prathul Srinivasan, who was a post-author on this work and then continued to do other work, and comes back to the original point that we need the right kind of representation. So in his PhD thesis, which was about representations for view synthesis with deep learning, he started by just predicting the light field directly. Then he did a bunch of work on multiplane images, of which this is local light field fusion. Multiplane images can be thought of as a sampled volumetric representation of the scene. Effectively, they're writing the scene as a volume, 3D volume, where you've broken it into discrete planes, and therefore you're sampling the 3D volume along planes in the depth dimension and along pixels in X and Y. So now the question is, why not a continuous volumetric representation? So the following year in 2020, we wrote this paper on neural radiance fields, which nicely enough actually received the Frontiers of Science Award last year. Bit out of order, but we'll take that. And I'm going to play the video for this.
We present neural radiance fields, or NeRF, a new method for representing complex scenes that achieves state-of-the-art results for view synthesis.
Can you hear this at the back?
Given a set of input images of a scene, which in this visualization is a Lego bulldozer, we optimize a volumetric representation as a continuous function which is defined for any 5D coordinate, consisting of a location and view direction. We parameterize the scene representation as a fully connected deep network that takes in a single 5D coordinate and outputs the corresponding volume density and view-dependent emitted RGB radiance at that location. We then use techniques from traditional volume rendering to composite these values along a camera array to render that pixel's color. Since the rendering process is fully differentiable, we are able to optimize the scene representation by minimizing the error of rendering all camera arrays from a collection of standard RGB images. Our method is able to reconstruct high-quality novel views from a sparse set of input images of a scene. Our strategy outperforms prior work that also represents a scene within the weights of an MLP, as well as prior work that represents a scene as a set of multiplane images or as a discrete voxel grid. Here, we visualize additional results across a wide variety of real-world scenes, each captured with 20 to 80 input images. Our neural radiance fields are able to render photorealistic novel views of scenes with fine geometric details and realistic view-dependent effects. We're able to capture all of this visual complexity in just the weights of a simple, fully connected network, requiring only 5 megabytes of storage for each scene. We can visualize the detailed view-dependent effects captured by our representation, such as the sharp reflections and specularities on this car, and the glossiness of this room's television and conference table. Our representation captures high-quality scene geometry, such as the details on this red flower, and complex occlusion effects in these tree leaves and ornaments.
All right, so then couple of years later, the NVIDIA researchers, Thomas Mueller and colleagues, made the neural radiance field method effectively interactive or even real time. So instead of taking many hours to train a model, they could do it in a few seconds, followed by real-time rendering. This was named as one of Time Magazine's top 200 inventions of the year. And this is effectively the way it works in real time, right? So it trains in a few seconds, and thereafter you can do real-time rendering. Last year, Bernhard Kerbel, George Dritakis at INRIA introduced 3D Gaussian splats, which represents the radiance field actually not using any neural components, just as a combination of Gaussians to represent the radiance field, and where the Gaussians are composited using a standard rasterization architecture. This enables, again, these very realistic and immersive experiences with these scenes with very complex foliage and rendering at 60 frames per second. So these techniques have now been widely used. Here is an example of using neural radiance fields for what we refer to as creating digital twins, completely realistic visual representations, in this case on the factory floor. Moreover, with the release of the instant neural graphics primitives source code, ordinary users can try it out. Here's someone who used a drone, I guess, to get their original image and was able to create a neural radiance field from that and then post it on Twitter. So this is the way the modern world works, right? So here is an example. And since this is, again, a volumetric radiance field, it can handle furry objects, and you can even zoom into your pet. Again, just an ordinary user posting these results on Twitter. This is also the era of large language models, and there has been work on using text-based editing on neural radiance fields, and more broadly seeing these representations as a bridge between 2D generative AI and where you have tons of data and 3D. So this is work from Berkeley. I'm not involved in this, from Ik and Anju Kanazawa and Alyosha Efros. Here are some examples where you can edit now, effectively do these text-based editing in 3D instead of only on 2D images. The original authors of the NERF paper, the student authors, have gone on to work at startups like Luma AI and Google, where these techniques have been used for Google Street View. Luma AI even has a NERF. You can capture images with that. Actually, last year, an hour before catching my flight after receiving the Frontiers of Science Award, I used the Luma AI app to make a NERF of the NERF trophy. And this you can find on my website. But let's come back to the original question that was posed in the local light field fusion paper. How do we achieve robust high-quality performance with sparser casual input view sampling? So local light field fusion said with 20 to 50 images, and NERF has used similar kind of images to produce high-quality renderings. But how far can you push this? Now, in work that will be presented at SIGGRAPH this year with my PhD student Kaiwen Jiang, we have developed a construct-optimized approach to sparse view synthesis, where we take out one of the properties that has been required for these view synthesis methods, which is accurate calibration of the camera or pose. So we no longer need that. And you can see if you compare our method to 3D Gaussian splatting and instant neural graphics primitives, even with as few, even with 3 or 4 views, but especially with 6 views, you are actually able to capture fairly high quality results and from just a very sparse set of views. So this brings up, why not push this to the limit? What can you do from a single image? It's actually a very popular topic. If you went to the evening of computer science, there was a talk from Tencent about the vision language model prompting with an image in order to get a 3D shape. I'll talk about some of those results later, or similar kind of results. But 7 years back, Prathod Srinivasan, who is the first author on this paper, had this notion of, like, for light-filled cameras, can I do this? Can I synthesize a 4D RGBD light field from a single input image? And he was actually able to, in the specific category of plants and flowers and also toys, he was actually able to get fairly dense 4D multi-view depths from a single input image, from which you can actually, for this narrow baseline light field, not these broad range that we showed earlier in the talk, but for a narrow baseline, you could actually produce pretty realistic results from a single image. Now, today, that work has completely been revolutionized by the advent of diffusion models, which enable you to train on like 5 billion input images. So I never thought that single image view synthesis would work outside of category level training. But now you can do it fairly generally. And so here is an example on text condition diffusion models where, I mean, you can create an image, but from the image you can actually create the full 3D shape. And this is from my colleague Hao Su, a sequence of papers where you can see that effectively, I mean, like you can use this even for text to 3D or image to 3D. And most recently, this work from Google researchers, Create Anything in 3D, where again you can do text-based or you can give it a single input image, and giving it the single input image shown here, you can create these kind of 3D and immersive visualizations, all from a single input image. So this is an area that has now really exploded, and we are beginning to get some really nice results even from a single image. You can think about the applications of this from a photography perspective. We can take all of our legacy photographs in our 2D album and now be able to view them in 3D, be able to have immersive experience, be able to put them into augmented and virtual reality applications. I just want to briefly talk about one work in this space that we presented at SIGGRAPH last year, which is the idea of creating personalized avatars. Now, we've seen a number of methods from Vision Pro from Apple, the codec avatars from Meta, Project Starline. Many of these are headed by my alumni, but they require multiple cameras, light stage capture, or depth information. So what can you do from a single input image? We were able to develop a technique with my PhD student Alex Trevethick, collaborators at NVIDIA, where you can take images just from a standard mobile phone and just processing one image at a time in real-time frame rate, 60 frames per second on a consumer graphics card. You can recover a radiance field, which allows you to change your viewpoint and recover depth. And the nice thing about this is that there is no synthetic or real data required for training. So everything is coming from a GAN model. You don't have to render faces. You don't need to acquire information in a light stage. So you can do it for any category for which you have a GAN model. We'll show examples later of cats as well. So here you can see an example. It's just running on each frame individually, and it is running at real-time frame rates. And it's not bothered if he puts on headphones or he puts on glasses. You see the input, but then you can change the output to a normal view, and you can also recover a depth in the scene. So here he is putting on glasses. So here you see some examples, and even, I mean, if you have paint on the face, etc., it still works fairly well with complex hairstyles, with babies, and even with dolls and things that are clearly not in the original data set. You can even apply it for paintings, and so this enables you to take a 2D painting and be able to now see it in 3D. Moreover, you can use it to lift text-based avatars to 3D. Again, these representations are a bridge between 2D and 3D. You use your text prompt to create a 2D image, and now you have your 2D image. You can apply our live portrait technique to create 3D from it. So putting these together, you can go from text to a full 3D avatar. And one of the goals is to use a method like this in 3D video conferencing, where in this case, this was shown in the SIGGRAPH 23 Emerging Technologies booth. And what the collaborators at NVIDIA did was that they were able to actually render the image onto a light field display. And the hope is that this can give you the next generation of AI-mediated video conferencing, where you can have immersive presence with the person that you're conferencing with. So to conclude, sparse sampling is key for view synthesis or image-based rendering, because in many practical applications, you're not going to be able to sample densely and take thousands of images and meet the Nyquist rate. Local light field fusion presents a rigorous, mathematical, robust solution, which provides the guarantees of sampling rates with a 4,000 times improvement on the naive Nyquist sampling rate. Note that the deep learning to create the multiplane images is almost an aside, and if you had an alternative method to create it, you could use it. It's really one paragraph in the paper. The core contribution is really a sampling theory. At the same time, this is one of the few works within the kind of deep learning space that actually provides rigorous bounds for when these methods work versus don't work, and gives you rigorous bounds for when to sample and where to take the images. Neural radiance fields and extensions have transformed view synthesis now. Effectively, NeRFs rethink the notion of 3D geometry with this kind of soft volumetric model. And if you're interested, the article I wrote for the Frontiers of Science Award last year talks about NeRFs as the new 3D geometric representation. And this has also led to many applications well beyond computer graphics and vision. I mean, in astrophysical processing, in metrology, and many other places where you can just represent things with a volume, whether or not they're actually a 3D shape, and you can have this neural or Gaussian splatted representation of a radiance field. There has also been a substantial work on sparse view synthesis for neural radiance fields and related methods, even from a single image. And the single image methods, of course, use modern diffusion models. Those are the state-of-the-art methods for single image methods. But I showed at the end of the talk that you can get quite amazing results today, even from a single input image. However, there is one thing that is missing, that the nice analysis and guarantees in local light field fusion have been lost. So I don't think any of the subsequent papers has actually developed a theory claiming that the results are optimal. So even though in practice we have been able to get down to even single image synthesis, there is no theoretical bounds or guarantees. And that does remain an open question about whether such bounds can be derived for modern radiance field-based methods. Of course, we would always like extensions to dynamic scenes. That remains, I think, a major challenge. May also relate with techniques for generative AI of videos like Sora. And light transport acquisition, everything I've talked into has baked in the lighting so that you're only doing view synthesis. We would ideally like to recover the reflectance properties so that you can also relight the scene. Finally, acknowledgements. The students in the early light field papers, the italicized ones, are authors on this paper, collaborators, and the funding agencies. So thank you again, and happy to take questions.
Many thanks for your exciting, very beautiful, fantastic talks. And anyone have any question? We have 15 minutes.
Very nice talk. I have two questions. The first question is, if you have flash rule, if the scene has dynamically changed, you have to sample continuously in order to synthesize views over time.
Yes, so again, I mean, the thing is, ideally, okay, so if you sample with multiple viewpoints across time, then you can reconstruct, I mean, each frame independently or do something fancier to reconstruct the full 4D volume. The more interesting thing is if the scene is changing dynamically while the camera is moving or the camera is static or the camera is binocular, then you're sampling in some sense a line or some structure in this time-varying space. And from that sparse sampling, you want to be able to reconstruct the scene. And that is the dynamic scene challenge, right?
I see. The second question is, the reason why I asked, I'm not working in computer graphs for the ones who worked on it 20 years ago, but later switched to the The second question is about the view synthesis. You mentioned that sampling is the key issue in the view synthesis. But based on my understanding, your view synthesis only considers the current scene. You never take the prior knowledge about what these things are, about knowledge about these objects and their properties, all these things.
Yes.
All this proper deep learning can help you, right?
Yes. So this work and most of what I presented is not taking any information about the semantic content of the scene. However, the single image methods that I showed most recently, so even our personalized avatar work is trained in a GAN model. So it has a lot of information baked in on what faces look like. And something like this, I mean, like without any information about the objects, you're not going to be able to do this, right? So here you have the knowledge of a diffusion model on what objects look like semantically and how they are. And this is the missing piece of information that has enabled these kinds of single image techniques to do it, right? So without any semantic information, this is hard, right? Yeah.
Then probably I have another question. Is like, so what do you think the major problem about diffusion-based method? It's quite slow, right?
Well, so I mean, that's something that I think will be improved. I think fundamentally the issue is, as good as these methods are, from a single image, you don't have the information to get the full scene. And these things can probably do a pretty amazing job, but I mean, fundamentally the information is not there. And in fact, I mean, we have tested these things. As you take more views, you do actually get better results, right? So it is actually necessary. And so the question will become that certainly you should leverage semantic information when it's useful, but you still will want to take multiple views to reconstruct the scene. And within that context, having a sampling theory or having some notion of what the error will be is a potentially useful thing, right? And even if you don't have that, you would want a method that gradually increases quality as you sample.
Okay, thank you. Another question?
Thank you for the beautiful talk. I think you mentioned at the conclusion that you couldn't get like theoretical bounds for the NERF method.
Yes.
So what is the difference between NERF and the method you talk about, like in the first half of the part?
Well, so in the case of local light field fusion for multiplane images, we have a theory of what the frequency spectrum looks like. We have a theory of disparity, and we can kind of develop Nyquist-like sampling criteria. For radiance fields, you are kind of integrating a volume where we don't really have those notions, and perhaps somebody should actually derive what the equivalent theoretical properties are. So that is an open question for the community. And I mean, like even here, if we didn't have the SIGGRAPH 2000 paper, we didn't have the theoretical analysis of light fields, it would be a hard bridge to go down. But For radiance fields, we haven't had that so far.